past few years, researchers in optomechanics have been investigating the cooling by light of small mechanical oscillators. Several groups have succeeded in cooling to the quantum ground state, or close, using different experimental setups.
Here we present a theory for a system where the equilibrium position of the oscillator is slowly modulated in time, while it is simultaneously cooled in an optical cavity.
One motivation is to understand experiments where the oscillator is levitated by a light field.
A levitated oscillator, supported only by the light field, is largely insulated from environmental heating and decoherence. One hope is that it might allow new types of quantum-limited sensors, such as accelerometers or for detection of weak forces.
Inside the ring, we magnify the inner region of the cavity. Initially, the particle moves freely, but it can become trapped and localizes in a single optical well. If it cools sufficiently, its motion can be hard to measure.
Fortunately, a Fabry-Perot cavity offers exceptional sensitivity in detecting motion. The LIGO experiment, which detected gravitational waves earlier this year, detected even displacements which are a small fraction of the diameter of a nucleus. So, even if the nanoparticle is in its quantum ground state, its motion can still be measured using the sidebands of the output light of the cavity. Typically, cavity sideband spectra are at a similar frequency to the mechanical oscillator. However, there has been a long-standing technical bottleneck holding up attempts to cool levitated nanoparticles. For quantum cooling, the nanoparticle needs to be in ultra-high vacuum. But as the pressure drops below 1 millibar, the particle can be lost.
In the experiments in our group, a Paul ion trap inside the cavity offers a safety net to prevent particle loss. But the ion trap field is an oscillating field. Its main effect is to vary the mean position of the oscillator in time.
When the particle is harmonically driven, its equilibrium position varies in time, and the particle does an excursion across the optical well. When the particle is at the linear region of the optical well, the coupling is maximum and the mechanical frequency is minimum. On the other hand, when the particle sits at the bottom of the well, the coupling is minimum and the mechanical frequency is maximum. And that's how you get the simultaneous and out-of-phase excursion in G and omega m.
As a consequence, the output light spectrum is no longer similar to the mechanical oscillators as for the standard optomechanics case. We term these observed features split-sidebands. A common feature is a pair of twin peaks, not at the mechanical frequency, but on either side of it. However, for particles trapped away from the center of the optical trap, the higher frequency twin peak is suppressed.
Trapping away from the center of the trap gives the strongest cooling, so it is important to understand this regime.
We model this behavior by starting from the standard linearized optomechanics Hamiltonian, but allowing both the light-matter coupling as well as the mechanical spring constant to slowly oscillate in time.
We develop a mathematical model.
And we explain also the underlying physical picture.
We investigate the behavior of the spectra in the quantum limit. We analyze the suppression of the higher frequency twin peak and obtain an expression for the ratio between the two peaks.
Split sidebands are not just a feature of nanoparticles in the Paul trap. The effect is generic to any other optomechanical setup with a modulated coupling constant and frequency.
Hopefully, our experiments will be able to detect split sideband spectra, including their behavior in the quantum limit.